So my name is Jérôme de Lauzon. I work in the research department of Bureau Veritas. And my presentation will be about the couple eigenfrequency analysis of floating wind turbines. So similar to what César just presented, but a slightly different approach. So maybe fast on this one, but of course you have to check the vibration frequencies of the tower when you design it and when you design the substructure. And the eigenfrequencies of the model you use for the integrated load analysis, they should be as precise as possible. You can include a bunch of effects in this analysis. So the added mass, the flexibility of the tower, orientation of the rotor nacelle assembly, the flexibility of the blade, the mooring stiffnesses. And you have different software that you can use for doing this. The first one is the hydroelastic tool. So in case of BV, it's Opera. And I will focus on another tool that we have used for this kind of analysis, which is called Homer, that allows to perform the full hydroelastic couple analysis. So to take into account both the hydrodynamic added mass and the flexibility of the floater in a consistent way. So in this Homer software, the basic idea is to use what we call generalized modes approach. And basically, instead of solving the sea-keeping motion equation on the 6 rigid body degrees of freedom, we add a number of natural vibration modes obtained typically from finite element solver. One back. Sorry. So you will decompose the motion on those 6 plus n modes. So here, typically 4 vibration modes of a floater with two towers. On the hydrodynamic parts, the idea is to solve the flow of the around the floater using a linear potential flow model. So in frequency domain, using harmonic wave excitation. And then we use the 3D boundary element methods to solve diffraction and radiation boundary value problem. And the key point in what we do here for hydroelasticity is that we will solve additional boundary value problems for the vibration modes for the radiation of those additional modes. So instead of solving 6 radiation problems, we'll solve 6 plus n radiation problem. Okay. So once we have solved those boundary value problem, we can have the different hydrodynamic coefficients. So we have the added mass A, which depends on the frequency, the radiation damping B, which also depends on the frequency, and then the forces on the right-hand side of the motion equation. And in this motion equation, all the matrices and vectors are not 6 by 6, but 6 plus n times 6 plus n. Then to perform the model analysis, the couple eigenvalue problem, we do what we typically do. So we remove the excitation and the damping from the motion equation. And then we have a system that we can diagonalize. And here we have to do this for each frequency because the added mass depends on the frequency. So for each frequency, we solve a different problem. And then we obtain the resonant frequency when the frequency used for the added mass matches the frequency that we have used for the added mass. And this is what is illustrated on the right-hand side. So we have on top, you have the added masses for the 4 modes, elastic modes that depend on the frequency. And then in the bottom, you see we try to match the frequency that is used for the added mass on the x-axis and the eigenfrequency that we solve using when performing the diagonalization of the system. Okay, next. So the example is the same as the one César just presented. So we started from the ANSYS model and translated it to Nastran. Here the RNA and the blades are modeled by a mass element, which is connected then by a rigid element to the top of the tower. And the water ballast as model as mass and rigid element as well. And then we can perform the model analysis in Nastran to obtain the 4 first modes, which we see on this slide. Okay. So then we can use our Homer tool to include the added mass effect. In this particular analysis, we didn't take into account the mooring stiffness, but it could be done if it's necessary. And then we did the same analysis with 2 assumptions for the floater. So the first one, which is a flexible floater, of course, what we want. So if you look at the first bending mode on the right-hand side, you see flexible floater on the left, and then rigid body floater on the right. And then we can compare those values to the measured values. So the first 2 lines are the fore-aft and side-side modes for a flexible floater. So you see the decrease in frequency when you add the added mass, so from 0.84 to 0.65. And if you compare this with the rigid body assumption, so the 2 last lines, you see, of course, a lower frequency compared to the rigid floater assumption. And so you see that both aspects, of course, are necessary if you want to match what is measured. If you do a rigid floater assumption, you will be too high. And if you don't take into account the added mass, you'll be too high as well. Okay, so this was with a fully dedicated tool for hydroelastic analysis, but whenever we want to do the actual analysis in integrated loss analysis, so for instance in BV Opera tool, you don't have the flexibility of the floater in the general case. If you want to do if you want to use a hydrodynamic database, it's not possible in general to model the floater as rigid. So here the tower is modeled with lump mass. And in Opera, we use the same model both for the time domain analysis and for the eigenfrequency analysis. Okay, next. Bon, il y avait une super mention. So in Opera and in other software, in general case, again, only the tower can be flexible. So of course, you will not get the correct result for the strength assessment. So on the right-hand side, you see the modeling. So you have, okay, no, so sorry. So the idea is to calibrate this model so that the eigenfrequencies will match the real eigenfrequencies. And in Opera, for this, we use a virtual tower, which is a slightly different approach compared to OpenFast. Here, we will not modify the existing tower, we'll just add another element. So on the right-hand side, you'd see the rigid floater, the flexible tower on the top, and the RNA, of course. And here, we have added another beam element that connects the rigid floater to the bottom of the tower. And by doing this, we can adapt the properties of this beam to match the target eigenfrequencies. And so, well, in conclusion, so we have this Homer tool, which is a robust and accurate hydroelastic coupling method. We use a generalized mode approach, which allows us to consistently model the full flexibility of the floating wind turbine, so including the floater. We compute the added mass for all the modes and for all frequencies. If needed, we can add, of course, mooring stiffness, for instance, for TLPs. And it's a simple and consistent method. We don't have to do any trick to do it. So we really solve the full hydroelastic problem consistently. Next. Okay. And the idea is that this full hydroelastic solution can be used to calibrate the model in the coupled simulations. So in Opera, we use what we call virtual tower to connect the floater with the tower using this fully flexible solution as a reference. Of course, what we've seen for this particular example of the Zefyros, is that if the flexibility of the floater is very important, at some point it will be hard to match those modes, those vibration modes, using this virtual tower solution. So for the first mode, mode number 7 on the picture, you can do it. But for instance, for the higher frequency mode, like mode number 9 here, you see a big deformation of the floater, and so of course it's not with a simple trick that you can model this. So for the future, we think it would be possible to implement the same generalized mode approach in the ILR software if it's something that becomes necessary, and especially for if the floaters become larger and larger and flexible, more flexible as well.